Okay, for this section, we're going to see if we hopefully have sense enough to do these in JASP. So, as soon as I get this out of the way, we're going to be using mainly this statistical analysis JASP book for these because it gives a great step by step guide and it gives a fantastic way to write up the results at the bottom. And we will start doing that soon. Um, I think you'll have four total little case studies where you'll have to figure out which test to use. Um, Solve the problem and write up the results, and they're not that hard. So starting here, and this the other textbook kind of goes off. There's a lot of good information, but it kind of leads you way down some windy paths. So read them for the information on hypothesis testing, but yeah, don't get too caught up in them. So we're going to be starting. We can start at page 43. We'll look at what an effect size is and how to calculate it. One sample t-test. We'll skip the binomial and multinomial. So uh, we're going to go through all and we'll go through all the assumptions for the one sample t, two independent samples, and paired samples. The main assumption for any t-test continuous dependent variable. And for one sample, comparing seeing if the mean of that population based on the sample differs from a set benchmark or, or hypothesized mean. So we got a certain standard or historical value. We want to see if it's different. We may want to see if it's less than or greater than. For right now, we're just testing the difference. So that's got to be a dependent variable, normally distributed, usually randomly selected, and independent, making sure there's no other outside interference, acting on it. So I'll show you how to test these assumptions for normality. For the two sample, there's two different ones. For the independent t-test, we have studentized, um, which you the assumption there, in addition to all these, that we have independent samples not related to each other, normally distributed with large enough sample size to matter, um, and yeah, normally distributed. We also are assuming that the variances are similar or equal, similar enough to be assumed to be equal for both populations. So remember, for a t-test, we don't know the population parameters, and usually in business we won't. So even if we do know, a lot of times we'll still use a t-test, simply because that's what all these are set up to do. So uh, if we determine that the variances are different, that's when we won't use a studentized t. We'll use a Welch correction, which is a different kind of t. Basically the same thing. It just makes an adjustment for larger variances, that may cause, more differences. Then we will learn for a paired sample, we're just looking at two within samples. So it's going to be like a before and after where each respondent tests you know, before and after the manipulation of the change or whatever, or rather than having whereas an independent sample, we may have a control group versus um, a manipulation or an action, as long as they're both randomly assigned to the groups, or we may just be comparing two different groups of the same variable to see if there's a difference. For a paired sample, we got responded at time one, responded at time two, and we're seeing the difference. And rather than comparing for the paired sample, rather than comparing the means of each group to determine if the difference is significant, we're taking the means of each line and then taking the mean of the differences to compare. So by doing that, we're controlling for any outside factors by using the same respondent at time one and time two. So it's an internal sample. So I'll show y'all how that works when we get there. And if that one's not normal, then we'll use a Wilcox assign rank. If the two independent samples are not normal, we can use a Mann-Whitney U. So and basically those use medians instead of means. So we can go ahead and start by looking at our effect size. And these are different effect sizes and ways that we interpret them. So for everything we're doing this week, coincidence D is going to be what we need for parametric, and we'll be using rank by serial for somebody's typing in while I'm trying to record this. So we'll just wait. So rank by serial for non-parametric, but mainly what I want y'all to know is the parametric. So because we're going to be dealing with normal distribution most semesters. So anything less than 0.2, it says trivial, is probably, even if it shows significance, the amount of the difference, even though the difference may always be there, and that's what significance basically tells you, the amount of the significance may not be large enough to make a difference. So it's going to be too small to matter. A small size, 0.2 and greater, is going to be small but meaningful for business decisions. Medium, 0.5 to 0.8, and then anything over 0.8 is very large. And, so the larger this effect size, the lower sample size you can have and still have power. Your power to a given, sample size determines your ability, to detect an effect size at these levels. So it's all interrelated. For your beta. Remember, your alpha just determines the probability that you're willing to accept that the actual difference won't be there. And, the p-value is the probability of it not being there. So it doesn't necessarily give you a size or an impact, whereas an effect size gives you better than that. And your power tells you your probability of getting that result at the alpha level. So those are kind of the different terms we use and how we use them. So let's go ahead and load this one sample and try to knock it out really quickly. So the file we're going to be using here, one sample t-test. I have those loaded in somewhere within the week 4 introduction. I know it's a long one this week, but it's a lot to learn. It's going to start being longer and longer. So if you look here, example data from statistical analysis and JASP, one sample, independent, and paired sample. Those are the ones we're going to do, and those are the ones we're going to use. That's where you can get them. So download them, save them to the computer, and then we'll come to JASP and load them. So open computer, wherever you got them stored. I got mine stored in this file, so I'm going to scroll down. I've got them all because I went to GitHub and downloaded the whole thing. So here we got, I've got that loaded twice, do I not? We need one of them. So let's close one. All right, so he doesn't show, but I always do, is just go ahead and run descriptives and make sure I don't have any missing or anything looking terribly out of shape, because we scroll down, so we don't want to see any single digit numbers for height for, looking at centimeters, because these numbers are height in centimeters and mass in kilograms of adult males in the UK. And that's why we're using centimeters and mass in kilograms instead of feet, inches, and pounds like we would in good old US. So, and we're determining if these are different than the stated amount, 178 centimeters and 83.4 kilograms. So, now that we've looked and seen, we can go back and kind of got our descriptors here. We don't really need anything. We're just kind of seeing, making sure everything looks, plausible. We got some pretty low weights there, but we are testing if they've changed, so that's okay. If you wanted to plot all the differences, I mean, that's fine, but right now we're just mainly looking, nothing's missing what we got for our initial sample, so we can close this. Now we'll go to t-test and open one sample t-test. So we're going to test height first because that's what the book does. And you can tell right away we've got a very high T and very significant P. That's because we have not put, and I'm going to go ahead and name this one height. We haven't put our test value. We're testing against what, 178? Yeah, 178 exactly. That's where we put the value we're testing against. So now you can see that's dropped down because we're actually testing the actual difference. So first thing we got to do is test for normality, make sure we're good to go here, and we are, because this Shapiro Wilk, that's a test that you want to fail, and it even says right here, significant result suggests a deviation from normality. So right now we can tell that that's very normal. Excluding cases per variable and list-wise. This is what I didn't get to last week because it's only within certain tests. So per variable, that's what we call pairwise deletion, which means we're only deleting part of the pair that matters. So if we had one of these missing and not the other, we would keep the line so we could use it for height, but not for mass if that's one missing. Since we're only really testing the mean of one and its standard deviation, using those to determine a confidence interval to test against this 178. So we're taking the mean here, subtracting 178 from it, and seeing if it's different from zero. That's our actual null hypothesis there. Or actually, we're testing whether it's different from 178. But the way we do that to get our actual critical value, and we subtract one from the other and see if it's different from zero, because that's how we do our two samples. If we were testing if it's increased or decreased, we could use a right tail for increased, a left tail for decreased right here. But right now we're just testing if it's different, so we're using a two tail. Listwise deletion, if either one of these were missing, we would delete the whole line, which is what y'all have normally been using, either listwise. I showed y'all how to do mean replacement. We did a log transformation. We can't do imputation because it's not in JASP yet, or Jamovi, whichever one you're using. They're both the same with the exception of Bayesian, which we're not going to get to anyway. So, the location, this tells us our actual mean difference here. Click on the confidence interval. It tells the confidence interval for the distance. I always click that, even though the book does not tell you to, because if you wanted to know if it's at least a certain amount, if you want to know if it's at least 5 different, that's the only way you can do it, because this doesn't give you, unless you added 5, but then that's only going to be on one side and not the other. So this is really the only way you do it. Just tell if the upper bound or lower bound is at least. Here we don't have any difference based on our numbers here. So our effect size, based on our effect size, we don't have any effect whatsoever either. So even though these are different from these T, they're kind of going to work because if you got a stronger effect, you're going to have a stronger T, unless you just have a monster sample size. Then you can have a small effect with a larger T. You can click the confidence interval, but we normally don't. We just normally use what it is. Because if it's going to be low enough that a confidence interval matters, then it's probably going to be too low. If you had a effect size of like 0.2 or like 0.24, you might want to run that to make sure it's always. But if it's above it, we're going to go ahead and assume that it's small but meaningful. Here's our descriptives, so you can get the mean value, the standard deviation, standard error, and coefficient of variation for our sample. 23 sample size, so n minus 1 for degrees of freedom 22. That's where that comes from. Your T, like I said, is going to be your your difference over your standard error. And he said to go ahead and click your plots. I always click horizontal display on my rain clouds because I think it makes it easier to see. But as you can see here, the hypothesized mean is within this box for our confidence interval for the mean. If we wanted to actually see what that was, since it only gives us the confidence interval for the distance, we could go into statistics here and just calculate it, and that'll, that way you can see for height 175 to 179. So that's what this chart here, 175 to 179, that's our 95% confidence interval for the mean right here. So our actual hypothesized means dead in the middle, so it's not any different. This value would have to be out here or out here to be in the rejection range. This is the whole sample, but this is the confidence interval for the mean, and that's what we're testing. So that's how you do that one. So now he says go ahead and try the other one. So t-test, he said the book says just drop the mean and keep all the check marks, but I like to do them both. So we'll call this one mass. We'll load it, and first thing we have to do is we had 68 point what, or actually 83.4 is what we're testing against. 83.4. Why did that not work? 83.4 is our test value there. To use a student's T. Now you can do a z-test if you have the population, but normally we just using students. So, and we're just testing different for this one. We got to test for normality. Use a z if you know the population standard deviation. And you would have to enter it. Right now, we don't. So, we're using a T. PM excluding pairwise. Got our test value in. Normality. Although it's closer, we are still not significant. So it's normal. So we come over here, look at our location estimate. Again, I do always click those just so I can tell. You may want to know if you're at least 15 different, or if you're at least 10 different, yeah, you're good. Well, actually, no. You would actually be at least 7.4 difference. So our effect size, look, we got a very large effect size because you always look at the absolute value of this when you're looking at those, and anything above zero point 0.8. So we got an extremely large effect size due to the large actual difference, even though our sample size is fairly small. Um, Descriptives gives us, descriptive statistics here. If you only wanted to, look at those here and not use the actual descriptive plots or the actual descriptives in the. So here we're looking at our plots, and here you can see our hypothesized difference. Here's our confidence interval for the mean. So yes, it is significantly different. It's still on our rain cloud plots. Again, you can leave them that way. I like to turn mine sideways. So if it's outside this confidence interval, it is significantly different. Here we're in the rejection range, so we reject the null. You're 95% confident that you reject the null and accept the mean. So here's how you get that. So if you want to know how to get the actual power of these, you can go over here and click power, and it'll tell you. You can go ahead and enter if you want to determine the sample size required for, what was that, effect size 1.4. For a minimum, we usually want 80 power with an 0.5. So for a two-sided, we want no one sample T. So for a two-sided, our required sample size for that large would be 7 to detect, which is almost unreal. But if we were only looking for a medium effect size, we'd need 34, which we don't have. So let's look and see what power we have based on our. And you do this with any. I usually use it for a program called G Power. It gives me a lot more to choose from than this, so it is still useful to me. But for simple tests and stuff like that, it's nice that they put this in here in recent years. So we got 1.4. We're looking for 80 power, but we want to see exactly what the power is for one sample. Our sample size was what, 22, I believe, 23. So our actual power based on this, and it'll give you charts there and kind of see as it grows out. Power curve by N is actually useful. So we want to be in 80 power range. So based on this, we've got all the power we need because that effect is large. If we wanted just to pick up 0.8, we'd need 23. We'd have 95, 96% power. If we were just looking to pick up a medium based on this, look, we don't have 80 power. So, and that's how you do it. So, and you can also determine your exact effect size based on the desired power and that. Mm, so our effect size for a medium at 80 power, 61. So that's kind of how we do that if you wanted that. And now the only other thing on this one is what's useful here. We determine, now we need to know how to write these things up. So start and he'll tell you exactly what I just told you about how all those for both tests and here reporting results. Make sure you look at reporting results here. So for both of these, we're going to report the results of both. For one sample, they're very easy. You just tell whether or not there was a difference or whether or not one was significantly larger or smaller if you're using a left or right tail, or right or left rather. And then in parentheses, put your T for 22 degrees of freedom equals at your actual T, and that's your P. Then he puts, however, tested for significantly lighter than UK male population average, but we weren't doing a one sample over there. We were doing, I guess it didn't matter, but that wasn't what we were told to do, was it? 7.159. If we were doing, if we were testing, if they were, I mean, the T is not going to, it's still going to be the same because that's your actual test value. It's not going to change. Your P value would change though. Well, actually, your T value would change because it's the P is the probability of the test statistic, which is the difference over the standard error. But the probability is going to be twice as strong for one tail. So, I mean, I guess you could report it, but normally you just put different. They were significantly different if he told you to, but that's how you report it either way. Negative, I guess he's just determining based on the negative difference that it is lighter. Um, but normally, if you were testing to see if they were lighter, you would choose a left tail test. So that is one sample. We will come back in just a moment to do two samples.